Hi, this is Gary Millett, and this is ELE-110, Electronics for Technicians 1, the fall of 2022. And today we're going to talk about topic number 11, which is Frequency Selective Components, or C's and L's. In other words, capacitors and inductors. So let's get started. So the title of this slide is Frequency Selective Components, and up to this point, the only circuit components that we have been talking about are resistors, or R's. And we should note that the characteristics of a resistor do not change with frequency. I've got an asterisk there, and I'll come back to that towards about the very last slide of this presentation. However, there are two other common electronic components, the inductor, the symbol L, and the capacitor with the symbol C. And these things are frequency selective. That is, their characteristics change with applied frequency. So let's talk about the basic capacitor. A capacitor is a structure consisting typically of two parallel conductors, oftentimes called plates. These two conductors are separated by an insulating or dielectric material, and connecting leads are typically attached to the capacitor plates. Now, the capacitor can store energy in the form of an electric field if a voltage source is used to charge it up. You may recall when we talked about batteries, Ben Franklin had what he called Leyden jars, and they were basically capacitors, but he called them batteries. The capacitor is one of two passive frequency selective devices. Its characteristics change with frequency, that is the frequency of the signal applied to it. Capacitance is a naturally occurring phenomenon whenever there are two conductors in close proximity to one another. So here's a picture of a bunch of typical capacitors, and I have this equation here. Stored energy is equal to 1/2 CV squared. So if I apply a voltage to a capacitor and the capacitor charges up, which we'll talk about momentarily, there'll be an electric field between the plates, and there'll be stored energy in terms of that electric field. So on the right-hand side of this slide, you see the little description that capacitors store energy in electric fields that exist between two metal conductors that form the capacitor. This electric field takes time to be created, and thus the capacitor is said to charge and discharge as a voltage is applied or removed from the capacitor. If we take a look at these very colorful capacitors on the left-hand side, there are electrolytic capacitors. The big fat ones are electrolytics. There are many different other shapes, and there's actually some variable capacitors there where air is the insulation between the conductors that make up the capacitor. And the plates mesh with one another, but they don't touch. So here's a picture of the basic capacitor, and you can see that again, it consists of a couple plates with connecting leads on those plates and a dielectric, which is a fancy term for an insulator. The symbols over to the right-hand side, the capacitor is a solid straight line and a curved line, but they're not touching. The capacitor may take on many shapes and forms to maximize its capacitance, as will be seen later. However, in all cases, it's basically two conductors separated by an insulator. Note its circuit symbol shown here also. We talked about that already. So here's what we call a mica capacitor. That's figure 13.8, and basically it's constructed of many layers or sandwiches of foil, then mica, foil, mica, and then foil, as shown in this diagram. A stacked layer arrangement. The layers are pressed together and encapsulated, and two leads come out of the mica capacitor shown here. Excuse me. And mica capacitors are usually available with values from, say, 1 picofarad up to, say, 0.1 microfarads. Again, capacitors, you'll discover, tend to be very small in value compared to the unit, the farad, that we use to describe them. So here's a different type of ceramic disc capacitor, and you take a look at this. The ceramic disc capacitors can achieve higher values in a smaller form factor, and so it turns out we have two leads and a ceramic dielectric between a couple discs, so we call this ceramic disc. again, typical values up to several microfarads. Here's a different type of capacitor. It's a ceramic chip capacitor used for surface mounting on printed circuit boards. And you can see that there's a lot of layers of that, electrodes, ceramic dielectric, and so forth. An actual device is shown to the right. It's actually quite small, about 1/8 of an inch long, with solder contacts on either end, so it can be soldered to the surface of a PC board. Here's what we call a tantalum electrolytic capacitor, a typical teardrop it's called, tantalum. And you can see the structure on the right-hand side. There's sintered tantalum pellet, tantalum pentoxide is the dielectric, manganese dioxide, a solid electrolyte, graphite, silver. It turns out they're kind of complex. An interesting thing was they were very popular low voltage, high value capacitors. You could Google the fact that there was something called the capacitor plague from 1999 to 2007. Somebody patented these types of capacitors, and somebody tried to copy them, reverse engineer them, and it turned out that the dielectric that they came up with was not stable, and so a lot of equipment was built with the cheaper copied tantalum capacitors, and it turned out that they all of a sudden would go bad after about 6 months of operation and cause the equipment they were into, have problems, if not, fail. Here's an electrolytic capacitor. You can see here's a AL can insulating sleeve. There's a wound cell consisting of an anode with foil covered with an oxide, a dielectric, and so forth, a rubber sealing, terminal leads, and so forth. The construction is quite complex for electrolytic capacitors, but they can have higher values. So here is some pictures, a bunch of electrolytic capacitors and supercapacitors. So the electrolytics are on the left-hand side, and you can see there's various ways they get mounted. Then there's also surface mount electrolytics shown there. On the right-hand side is a GT cap ultra capacitor. It says it's 3,000 farads. The only trouble with this thing is that it only works at several volts. So it turns out that, again, the energy stored in a capacitor is 1/2 CV squared. Well, we made the value of C very large, but it turns out that the value of voltage V is quite low. But people are working on making higher voltage supercapacitors, and they would be useful for things like electric vehicles. Actually, to finish off that last slide, there are several buses that are electric buses that have supercapacitors that are involved with their operation. This slide shows variable capacitors, and since it may be necessary to change the value of a capacitor, variable capacitors are also available. And you might notice that each one of these has some type of little trim screw that you can take and turn, and it will change the amount of capacity in these trimmer capacitors, they're called. In figure 1316 there, it shows the variable capacitor symbol, which are two straight lines that don't touch with an arrow going through them, indicating that we can vary the amount of capacity. So what about capacitors in DC circuits? In DC circuits, we're going to say the frequency is equal to 0 hertz. So a capacitor will charge up in a predictable manner, that is, it's mathematically calculable when connected to a DC voltage source. The rate of capacitor charging is directly proportional to the value of the capacitance and the resistance in the charging circuit. The initial charging rate is quite fast, but declines as the capacitor charges up and the voltage across it increases. Eventually, the voltage across the capacitor will build up to the applied voltage. When the capacitor is fully charged, the charging current becomes 0. So this graphic shows, in this figure 1328, charging a capacitor. If we take a look at part A of that figure, you see it shows plates A and B, and there are free electrons on both of those plates. There's a battery, V sub S there, with plus and minus, and a switch. So the switch hasn't been closed yet, but if we move over to figure B, what happens is we close the switch and the positive side of the battery will attract the electrons away from plate A, and the negative side of the battery, electrons will spread out, more electrons will make plate B more negative rather. So plate A will become more positive, B more negative. If you go to C, what you discover now is it's fully charged, and what happens is the voltage across the capacitor is equal to the voltage of the battery, V sub S, with the polarity as shown, plus on A and minus on B. And if I take and open the switch now that the capacitor is fully charged, what happens is the charge remains on the capacitor if the charging source is removed. And a capacitor can stay charged for a long period of time. There may be mechanisms, losses in the capacitor. The dielectric may not be perfect, an insulator, and it might take and discharge the capacitor as time goes on. How about discharging a capacitor? Here we see that we have a capacitor in figure 1329 that is fully charged to 50 volts, with A being plus and B minus. Now, when the switch is closed, what happens is the charge can equalize. That is, the electrons from plate B can move around the circuit to redistribute themselves to the positive charge on plate A. And eventually what will happen is the charge will redistribute itself and be even on both A and B, and therefore there'll be 0 volts across A and B. Remember that voltage is the separation of charge. So the description here, when the switch is closed in the graphic shown here, the capacitor will discharge rapidly since there's very little resistance to oppose the flow of current. The voltage across the capacitor will go to 0 when fully discharged. Now, another graphic here shows how the voltage across the capacitor can't change instantaneously. So this is figure 1329, and the top one, A, charging, the switch closes, and the current jumps to a maximum at the instant the switch is closed, then it decreases. Voltage is 0 at the instant the switch is closed, then it increases. So the capacitor can instantaneously have a big jump in current flowing to it and away from it. Notice, by the way, here's a common fault people don't realize, that no current flows through the capacitor. Remember, the capacitor are 2 parallel plates separated by an insulator. So there's no electrons flowing through the capacitor. What's happening is they are flowing through the wires that are connected to the plates of the capacitor. So again, we close the switch and there's a big jump in current all of a sudden because the capacitor acts like a short circuit. It isn't a short circuit, but acts like one. And then the voltage does not change instantaneously, but it will gradually go up, and as the current will gradually go back down. In B, we see that the capacitor is fully charged. There's no voltage across the resistor. The current in the meter there is 0, and there's a voltage across the capacitor equal to V sub S, the battery voltage. Okay, so then we take a look at C, and C is all of a sudden we're going to close a switch to discharge the capacitor. What happens now when we instantly close the switch? The current jumps to maximum at the instant the switch is closed, and then it decreases. The voltage decreases as the capacitor discharges. So again, there's a resistor there in C to take and limit the flow of current. The capacitor will not discharge instantaneously. It'll take some time. So again, ideally the current itself can change instantaneously, but the voltage can't across a capacitor. So this slide's called Current and Voltage During Charging and Discharging. And again, just bears repeating this. The voltage across a capacitor can't change instantaneously, but the current through a capacitor can change instantaneously. You go from nothing all of a sudden to something. A fully charged capacitor appears as an open to DC. A fully discharged capacitor appears as a short to DC. These characteristics of a capacitor give rise to many practical applications in electrical circuits and systems. So you might ask, is there any way we can figure out how fast this happens? Yes, we can. There's a thing called the RC time constant. So when a capacitor charges or discharges through resistance, a certain rate of charging or discharging occurs. This rate is known as the circuit time constant and is given by tau equals to RC. Tau is a Greek letter. So as an example here, a series RC circuit has a resistance of 1 megohm and a capacitance of 5 microfarad. What is the time constant? We discover the time constant would be 5 seconds. Now, the fact we know what the time constant is doesn't tell us too much, so we got to delve a little more into this. And here it is here with these charging and discharging curves. So what you see in figure 1330, part A, charging curve with percentages of the final voltage. So we know what the time constant is, and what will happen in one time constant is the capacitor will charge up to approximately 63% of its final voltage. In two time constants, 86%, three time constants, 95%, four time constants, 98%, five time constants, 99%, or essentially totally charged up. So again, these curves show how the capacitor charges or discharges. The curves are nonlinear, actually exponential in shape, and they represent the physical phenomena occurring. In one time constant tau, a capacitor will charge up to 63% of its final value or discharge to 37% of its initial value. And again, this type of phenomena happens often in nature. So if we look at graphic B here, we start at some initial voltage across the capacitor, and we're going to discharge the capacitor through a resistor. Notice the one-time constant goes down to 37%, two-time constants 14%, three-time constants 5%, four-time constants 2%, five-time constants 1%, and basically down to 0 at six-time constants. And you'd notice that those are the exact opposite, or I shouldn't say opposite, 63 and 37% add up to 100. If you look at 14 and 86, that adds up to 100. 5 and 95 add up to 100, and so forth. So you can predict, again, what the charge and discharge will be if you know one versus the other. So here's an oscilloscope display, and the circuit is being driven by the pulses in the top trace. And what you see is the charging of a capacitor during the time period that the pulse up above in the top trace is high, and then the pulse drops down low, and what you see is the discharging of a capacitor. So here I get this charging discharging type of sawtooth waveform of a capacitor charging and discharging when it's driven by a repetitious pulse waveform. Now, there's another thing that happens with capacitors and also inductors, and that is we have this thing called reactance. And reactance is the term we use for opposition to AC due to either capacitance or inductance. It's not quite exactly the same thing as resistance. Resistance is resistance to the flow of current, DC current or AC current due to a resistor. So capacitors and inductors have what we call reactance, which is their opposition to the flow of AC in a circuit that they're connected to due to the fact that they have to charge and discharge or build up a magnetic field and de-energize a magnetic field. So capacitive reactance we call X sub C, and it's the opposition to sinusoidal current, AC. It's expressed in ohms. So how is, and so here's figure 1343, and the higher frequency waveform A has a greater slope at a zero crossing corresponding to a higher rate of change. So how is X sub C related to frequency? Well, we note that the value of I is proportional to the rate of change of voltage. So it turns out higher frequencies will be different than lower frequencies as far as reactance. And from various rate of change relationships, one may deduce that X sub C is proportional to 1 over F. That is, it goes down with frequency. Furthermore, it may be shown that X sub C is given by this equation, where the equation is 1 over 2 pi Fc, where F is the frequency, C is the capacitance, and 2 pi is a constant. So this equation indicates that capacitive reactance is infinite at DC, because F would be equal to 0, and anything divided by 0 blows up to infinity, and then gets smaller as frequency increases. Matter of fact, as frequency gets very high, we say the X sub C goes to 0. So here's an example of capacitive reactance. We have a signal source, V sub S, it's AC. We have a capacitor of 0.005 microfarads, and it turns out they determine the value of X sub C, and the solution here is 31.8 k ohms. So a little capacitor has a opposition to the flow of AC of 31.8 k ohms, and we could use that to figure out what the current would be flowing in that circuit. So now we're going to switch gears and talk about inductors. The basic inductor with the symbol L. So a length of wire formed into a coil is a basic inductor. The terms coil and inductor are interchangeable in electronics. A current through a coil produces an electromagnetic field, and there's a symbol for the inductor is a basically coil of wire. So what happens when a current flows through a coil of wire? Well, what happens is magnetic lines of force around each turn in the coil effectively add together with the lines of force from the other windings to yield a strong electromagnetic field that surrounds the coil. And you can see this figure here, 14.1. A coil of wire forms an inductor. When there is current through it, a three-dimensional electromagnetic field is created, surrounding the coil in all directions. And you might notice that they show a current I going in the left-hand side and exiting the right-hand side. And it turns out because of that flow of current in that direction, we get a north pole on the left and a south pole to the magnetic field on the right-hand side. So what about energy storage in an inductor? Well, in an inductor, an inductor stores energy in the electromagnetic field created by the current through the inductor. The amount of energy stored is given by W is equal to 1/2 Li squared. Remember, for capacitors, 1/2 CV squared. So again, the voltage is what stores the energy in electric field in the capacitor. In the inductor, the amount of current is producing electromagnetic field, and that's what stores the energy in the inductor. So let's move on to the next slide. What about the physical characteristics of inductors? Well, the type of core material is extremely important in the determination of a coil's inductance. Types of core materials are non-magnetic cores like air, wood, plastic, and so forth. And those are just used as a form to be able to wind the coil on. Then there are magnetic cores like iron, nickel, steel, cobalt, and so forth. Magnetic materials are classified as ferromagnetic, and ferromagnetic materials usually have rather large relative permeabilities, is called. That's mu sub r, that increase the magnetic field. They actually magnify the magnetic field. What about the physical characteristics of inductors? Well, the inductance of a coil is proportional to the number of turns N, the cross-sectional area A, and the permeability of the core mu. By the way, air would have a permeability of 1. So figure 14.4 there shows a coil, and it has so many turns, a certain length, and cross-sectional area. The inductance of a coil is inversely proportional to the coil length. So inductance is given L is equal to N squared, goes up by the square of the turns, mu, which is again the permeability, A is the cross-sectional area, and L is the length. So here's an example. It says determine the inductance of the coil in this figure 14.5. Permeability of the core is 0.25 times 10 to the minus 3. And so it turns out that if you take and do the math there, you get 40 millihenries, a small amount of inductance. Henry is a unit of inductance. So there are all kinds of types of inductors, just like there were for capacitors. The first types of inductors had air cores. As technology has advanced, newer, more modern materials have been used to construct inductors and to improve their characteristics. So again, like capacitance, inductance is a naturally occurring phenomena whenever one has a wire conductor. And as soon as a wire conductor has current passing through it, it produces a magnetic field around that wire, which is, again, inductance. So this slide shows you different types of inductors. Inductors tend to be classified by the type of core material used to construct the inductor. and whether the inductance value is variable. So fixed and variable inductors are shown in 1410 there. Fixed is A, variable has a line, arrow through it, that's B. If we go down to figure 1411, inductor symbols, if I've got an air core, it's shown as symbol A there, or rather graphic A. An iron core has 2 bars next to it, and a ferrite core has several bars that are broken, dashed lines, if you will. And here's a picture of different types of inductors. Variable inductors provide a movable core which can be adjusted to change the inductance value. And so down in the bottom there, you see a bunch of variable inductors, and you would actually use a plastic stick, which is shaped in such a way that it can grab the core, and you turn the core and move it in the inside the inductor, so it's either in the middle of the coil of wire or moved to one side, and that will vary the inductance. So here's again a picture of various inductors, and inductors again store energy in the magnetic field that builds up around the coil windings. Like a capacitor, it takes time to either energize the magnetic field or to collapse it. Thus, the current through an inductor cannot change instantaneously. The inductor, like the capacitor, has a time constant associated with its operation. So again, you see various different types of inductors there. So what about inductors in DC circuits? Well, like a capacitor, the inductor will become energized when it's connected to a DC voltage source. The current through the inductor, and hence the resulting electromagnetic field, will build up in a predictable manner. The current buildup will be dependent upon the value of inductance and the amount of resistance in the circuit. The current buildup will be similar to the voltage buildup for the capacitor that we discussed earlier. Once the inductor current has reached its final steady state value, there's no induced voltage, and the inductor appears as a short. Energy is stored in the electromagnetic field as discussed earlier. There can be energy lost, would be heat, due to winding resistance. And again, a little graphic here, figure 1419, shows what happens as an inductor is powered by a battery. In this case, turns out we get a magnetic field around the inductor and energy stored equal to 1/2 Li squared. So what about the RL time constant? Well, the current cannot change instantaneously in an inductor. The rate at which the current changes is determined by the time constant. The time constant is given by tau, in this case, is L/R. And they do an example for a 1 millihenry inductor with a 1 k ohm of resistance. Turns out to be 1 microsecond for the time constant. So what about the energizing current in an inductor? Well, the current through an inductor will increase exponentially as shown here. And this is very identical to what happens with the voltage across a capacitor. In one time constant, the current will go up to 63% of its final value. So again, recall the charging of the capacitor shown previously. The inductor is analogous to the buildup. Well, the charging of the capacitor is analogous to the buildup of the magnetic field of the inductor. So we talk about energizing the magnetic field and then de-energizing it or collapsing it. So here's de-energizing current in an inductor. Current flow in an inductor decreases exponentially according to the circuit time constant, the collapsing of the magnetic field. And notice here, again, the 37% after one time constant, current will decrease to 37% of its initial value after one time constant. It takes time for the magnetic field to collapse, and it does it in an exponential fashion. This oscilloscope display of an RL circuit might be pretty intimidating to you if you take a look at it. The blue square wave is being applied to an inductor. So this oscilloscope display shows what happens when a square wave is applied to an inductor and resistor in series. So what happens? The voltage across the inductor is shown as the red trace. When the voltage is first applied, the voltage instantaneously increases, but then exponentially decreases as the current increases. When the input voltage changes polarity, the current spikes due to the rapidly collapsing magnetic field. This process repeats itself over and over due to the applied pulse waveform. So again, what happens is the current can't change instantaneously for an inductor, but the voltage can. And as a matter of fact, the voltage can exceed, as shown here, the voltage applied. And again, when all of a sudden the pulse flips its polarity, what happens is we get a spike, which again will decrease exponentially. So it's a little more complicated than the capacitor for a resistor and an inductor in series. So what about inductors in AC circuits? Well, inductors like capacitors pass AC, but an amount of opposition called inductive, with an amount of opposition called inductive reactance, which is again frequency dependent. Recall that the voltage across an inductor can change instantaneously, but the current can't. For inductors, this leads to the voltage leading the current by 90 degrees for purely inductive circuits. I don't think I mentioned before that what would happen is the current would lead the voltage for a capacitor by 90 degrees for a purely capacitive circuit. So here's phase relationship of current and voltage in an inductor. This is figure 1413, and again what happens is the current leads the voltage for an inductor. The voltage leads the current for an inductor. So B shows the phasor notation for I and V in an inductor. Again, a 90-degree phase shift. What about inductive reactance? Well, an increase in L increases the induced voltage, and a decrease in L decreases the value of induced voltage. So it turns out, using these particular equations, we can come to the conclusion that X of L is proportional to F times L, or on the equation to the right, X of L is equal to 2 pi FL. And it may be shown that, well, this equation indicates that the inductive reactance increases with frequency. So here's an inductive reactance example. In this case, we've got what? A AC signal source, V sub S, a inductor of 5 millihenries, and it turns out when they do the math here, at 1 kilohertz, the X of L value would be 31.4 ohms. So note that inductive reactance increases with frequency. There's the opposite of capacitive reactance, which decreases with frequency. So for an inductor, well, I'll probably get that in the next slide. I should talk about it then. So for an inductor at 0 hertz, the reactance looks like 0, and we go to infinite frequency, the reactance looks like infinity. So what about applications of C's and L's? Well, since the characteristics of C's and L's change with frequency, the reactance is frequency sensitive, we can make circuits that pass certain frequencies while not passing other frequencies. These types of circuits are known as filters. Two typical filter circuits are a low-pass and high-pass filter. If you've ever taken and played with a graphic equalizer on a radio or an amplifier, or have adjusted the tone on your car radio, basically low and high-pass filters are used to take and alter the sound of the music. A circuit with both capacitance and inductance can be used to either pass or reject a narrow frequency range. These types of circuits are known as band pass or band reject filters. So what about limitations due to capacitance and inductance? Since capacitance and inductance are naturally occurring phenomena, their effects can limit system performance. Stray capacitance can cause feedback pass that can cause systems to go into unwanted oscillations. Stray inductance can also cause unwanted circuit performance issues. So if one designs a circuit to respond to different frequencies, we call it an electronic filter. Filters are used in many electronic systems, especially communication systems. If stray values of capacitance and inductance cause unwanted circuit effects, we say that these effects are due to parasitic capacitance or inductance. And depending upon their overall effect, we will usually try to minimize any detrimental effects to circuit operation caused by, say, parasitic capacitance or inductance. So what about capacitance and inductance at high frequencies? These negative or detrimental effects tend to occur more at higher frequencies or at higher speeds of operation. High enough frequencies, our resistor will tend to exhibit both capacity. We have leads separated by an insulator, and inductance, the leads conducting the current for the resistor. Even the wiring between components becomes problematic at very high frequencies. And I think that's it for this presentation.